Good morning, students. Here the module 3 is covalent bond. The valence bond theory is available to watch in the earlier video. You can hear the molecular orbital theory in this session. Now, I wish to provide a thorough description of molecular orbital theory. The instructor of this video is Mrs. P. Arunajyoti, Assistant Professor in Chemistry, St. Joseph's College for Women. Construction of molecular orbital energy diagram is one of the most important aspects in molecular orbital theory. Certain compounds are not entirely explained by Vesper theory and valence bond hypothesis. We know that despite their accuracy in predicting bond characteristics, molecular orbital theory takes the wave nature of electrons into consideration while creating molecular orbital energy diagrams. Molecular orbital theory can explain the physical and chemical characteristics such as shape, bond energy, bond length, and bond angle of a molecule. They also aid in the prediction of a molecule's electronic spectra and its paramagnetism. These are the steps involved in the construction of molecular orbital energy diagram. Step 1, Step 2, Step 3, Step 4. In Step 1 is determine the number of valence electrons in total. You have to do in the step 1, that is determination of total number of valence electrons possessed in its atomic orbitals of both the atoms in a molecule. Step 2 is write the number of electrons in each s and p orbitals. You should ascertain how many electrons are present in each s and p orbitals. Recall that the n equal to 2 energy level, you know that it consists of a 1s orbital and 3p orbitals. For every molecule, ascertain how many electrons are present in the s and p orbitals. Suppose if you take one example like boron, it contains 1 electron in the 2p orbital and 2 are in the 2s orbital. Take one more example like fluorine contains 2 electrons at the 2s energy level, while in the 2p orbital it has a 5 electrons. Let us know about step 3. Complete the electrons. You should do the filling of the electrons in the correct molecular orbital energy diagram. Okay. When filling up of molecular orbitals, all the orbitals filling based on 3 principles. Those are Pauline's exclusion principle, Hofbauer principle, and Hund's rule. Okay, according to those 3 rules, we should do the filling up of electrons in the bonding and anti-bonding molecular orbitals from lower energy levels to the higher energy levels. The last step is step 4. Predict the molecule's properties using the diagram. For example, bond order and paramagnetism. We know that number of electrons in bonding orbitals is represented by Nb, while the number of electrons in anti-bonding orbitals is represented by Na. If Nb is greater than Na, then we can say molecule is stable. If Nb is less than Na, then the molecule is unstable. If Nb equal to Na, molecule is unstable. From this, we can define the bond order is half of the difference in the number of electrons in the bonding and anti-bonding orbitals. The formula for calculating the bond order is Nb minus Na by 2. By using that formula, we can calculate the bond order of certain species. If Nb equal greater than Na, then only the molecule will be stable. Otherwise, it is unstable. Okay, we know that bond order is always inversely proportional to the bond length. Okay, the next thing is finding of the magnetic property. Okay, we should find whether it belongs to the diamagnetic or a paramagnetic. If all the electrons in the molecule are paired up, then we can say it is a diamagnetic substance. If the molecule contains some unpaired electrons, then we can say it is a paramagnetic substance. All these are the steps. Step 1, 2, 3, 4 are involved in the construction of molecular orbital energy diagram. Let us see the different examples of homonuclear diatomic molecule. What are homonuclear diatomic molecule? When the bond operated between the two similar atoms, such type of molecules are called as homonuclear diatomic molecules. H2, He2, Li2, B2, C2, N2, O2, F2, Ne2 are the examples for homonuclear diatomic molecules. Here I given you two codes, 2121 and the next code was 1221. What are these two codes? What do you understand from these codes? These are the codes for better understanding that how to write the number of boxes for 2p bonding and 2p anti-bonding molecular orbitals in the central position. While writing the number of boxes for 2p bonding and 2p anti-bonding molecular orbitals, you should remember these codes. These are the codes implies that remembering of 2p molecular orbitals. Well, these codes would not be applicable for s molecular orbitals, only applicable for p molecular orbitals. The first code is applies to the species containing up to 14 electrons. For example, you can take H2 molecule, He2 molecule, Li2, Be2, B2, C2 and N2 molecule. The second code is applicable to the molecule containing more than 14 electrons. For example, you can take O2 molecule, 8 plus 8 total 16 electron. It is a species containing more than 14 electrons. So we should apply for O2 molecule is 1221 for 2p molecular orbitals. These codes may apply not only for homonuclear diatomic molecule. You can apply it to heteronuclear diatomic molecule or some types of ions. Moving to the next slide. The first example of homonuclear diatomic molecule is H2 molecule. H2 molecule is made up of two hydrogen atoms. What is the atomic number of hydrogen? 1. Its electronic configuration is 1s1. The electron of the hydrogen atom possessed in its 1s atomic orbital. When you combine 1s atomic orbitals of both the hydrogen atoms, we will get the molecular orbitals in the middle position. When you are doing the construction of molecular orbital energy diagram for any molecule, either it is a homonuclear diatomic molecule or a heteronuclear diatomic molecule, need to keep it in mind basic three things. What are those three things? The first thing is way of doing of construction of molecular orbital energy diagram and writing of energy order from lower energy levels to the higher energy level. The second thing is calculation of the bond order. What is the formula of bond order formula? Is number of electrons present in bonding molecular orbital minus number of electrons present in anti-bonding molecular orbitals by 2. You will get the bond order for any molecule by using this formula. The third thing is we have to find out the magnetic property of a particular substance. Means you should find out the magnetic property of the molecule, whether it comes under the paramagnetic property or a diamagnetic property. These are the three things need to keep it in mind. Let us coming to the our example, that is hydrogen molecule. Here you can look at the picture, two hydrogen atoms. These are two 1s atomic orbitals. When you overlap the two 1s atomic orbitals of the two hydrogen atoms, we will get the two molecular orbitals. This one is a bonding molecular orbital. The above one is the anti-bonding molecular orbital. It can be termed as sigma 1s bonding molecular orbital and sigma star 1s anti-bonding molecular orbital. The number of boxes from the both 1s atomic orbitals 1 plus 1, 2 boxes. Okay. On either side of the molecular orbitals, the number of atomic orbital boxes are 2. Okay. That is the reason the obtaining molecular orbitals are also equals to the 2 at the middle position. Then you should fill the electrons. How to fill the electrons? Based upon the three rules: Hofbauer principle, Pauli's exclusion principle, and Hund's rule. According to those all these rules, the first electron goes to the sigma 1s level, second electron goes to the sigma 1s level. The electrons get sped up. No more electrons at the anti-bonding molecular electron bonding orbitals. Okay, this is the way of doing of construction of molecular orbital energy diagram for H2 molecule. The next one is calculation of the bond order. Number of electrons present in bonding molecular orbitals are 2. And the number of electrons present in anti-bonding molecular orbitals 0. 2 minus 0 by 2. Answer is 1. 2 by 2 equal to 1, no? The getting answer is bond order 1. It shows that molecule is very stable since it has a positive value. The two hydrogen atoms are connected by a single bond. That is the operation of the single bond between the two hydrogen atoms in a H2 molecule. Okay. The third thing is what? Finding of its magnetic property. There are no unpaired electrons. All the electrons get paired up. No. No more unpaired electrons. It has a diamagnetic property. It belongs to the category of diamagnetic property. It is about the H2 molecule. Let us take one more example. The next example is helium-2 molecule. Helium-2 is associated with the two helium atoms. Helium atomic number is 2 and its electronic configuration is 1s2. Both the 1s atomic orbitals of helium-2 molecule overlaps to form two molecular orbitals, bonding molecular orbital and anti-bonding molecular orbital. Bonding always tend to occupy at the lowest position and anti-bonding tend to occupy at the highest position. The total electrons occupied at the two atomic orbitals of the two helium atoms are 4 electrons. Out of 4 electrons, 2 electrons goes into the bonding molecular orbital, that is sigma 1s, and the remaining 2 electrons goes into the sigma star 1s anti-bonding molecular orbital. After constructing the molecular orbital energy diagram for helium-2 molecule, the next thing is calculation of the bond order, whose formula is Nb minus Na by 2. The number of electrons in a bonding is 2 and the number of electrons in anti-bonding is 2. 2 minus 2 by 2 equal to, you'll get the answer for bond order is 0. Bond order of 0 indicates that no bond is formed between the two atoms. So there is no driving force for helium atoms to form the diatomic molecule. In fact, helium exists as a discrete atoms rather than as a diatomic molecule. We know that helium is a noble gas. Always it prefers to exist as an independent in nature. The bond order in a hypothetical dihelium molecule would be 0. Since there are no unpaired electrons, all the electrons gets paid up, no more electrons, unpaired electrons. So helium belongs to the category of diamagnetic substance. Okay, it has a diamagnetic property. It is about helium-2 molecule. The other example for homonuclear diatomic molecule is Li2 is formed by the combination of two lithium atoms. Each lithium atom shows its atomic number is 3 and its electronic configuration is 1s2, 2s1. You can examine the picture. Each lithium atom has 2 electrons at 1s level and only 1 electron at the 2s level. First of all, you will do the overlapping of two 1s atomic orbitals of both the lithium atoms. We will get the two molecular orbitals sigma 1s and sigma star 1s. Molecular orbitals involved in bonding have 2 electrons, while those involved in anti-bonding have 2 electrons. After construction of a 1s atomic orbital overlapping, you'll go for the construction of 2s atomic orbital overlapping. Each 2s has 1 plus 1 total 2 electrons. These 2 electrons went into the sigma 2s bonding molecular orbital. Sigma star 2s remains empty. It has no paid electrons or unpaid electrons. The next thing is calculation of the bond order. Number of electrons in bonding is 4 and the number of electrons in anti-bonding is 2. 4 minus 2 by 2, 2 by 2. The answer is bond order 1. The molecule is very stable since it has a positive value. The two lithium atoms gets connected by a single bond. You'll get the bond order is 1. No, that is the reason single bond is present between the two lithium atoms in lithium molecule. Since there are no unpaired electrons, Li2 molecule is considered as a diamagnetic substance. All the electrons gets paid up in Li2 molecule. That is the reason it has a diamagnetic property. What I have done here, I done a construction of MOED and writing of the electronic configuration of Li2 from lower energy levels to the higher energy level, that is sigma 1 is occupied with the 2, sigma star 1 is occupied with the 2, sigma 2 is occupied with the 2, sigma star 2 is 0. No need to write this. Then calculated bond order. After calculating the bond order, you will go for the finding of magnetic property. Okay, this is about the Li2 molecule. Coming to the next example. All the images in this video have been taken from Google Chrome. Thank you.